recording is started. Let me load the slides now. Hello, Narendra. Hello. Hello.
Hello, sir.
Yeah, Narendra.
Yeah,
Are
good
you?
evening, sir. Good evening, sir.
Yeah, good evening. Are you able to hear my voice properly?
Yeah, sir. It is
Oh,
clear.
okay,
Your voice is clear.
okay. Uh, 1 second. I'll just try to load the slides. I think we should wait for some time so that
Okay, sir.
maybe
Uh,
maybe few more will join.
Actually, sir, today I was facing a problem as your meet is with a Google team.
Mhm.
Uh,
No. Actually, I tried with Google Team once, but
mhm.
there is some problem. I don't know why, but it was not happening properly. So I changed it
Yeah.
to Teams. Hmm. So 1 second, I'll just try to load the file here. Are you able to see the slides, Narendra?
Yeah, sir.
Okay, good. So we'll
Sir,
wait for.
sir, I have more conversation with Google Meet. Uh, that's
Do you have
why. Uh,
Do you
nah,
have any issue with the Teams or
no, sir, no, sir.
no? I actually tried with Google Meet, but
Yeah. Uh-huh.
there was some problem. I could not figure it out.
Mm.
So I started with the Teams. I am more habitual to Teams actually. That's why.
Okay, sir. Huh.
Anyway, so more people are here. Kanishk,
Mm.
is it Kanishk or Kanishka?
So good evening, Karichka Singh.
Okay. Good evening. And one more is 21A95A0329. I think it's from mobile. I think so. Anyway, we'll wait for some time. Let's say 4 5 minutes more. If some other people join, that's good. Otherwise, we'll carry on. And as far as I remember, uh, Abhik have you attended his session last weekend? Any one of you?
In the last week, I attended the class.
Abhig Deb, he might have taken the
Yeah,
class.
sir. He's from ISC Bengal.
Yeah. He's
Yeah.
my mate only. We are from same
Acha,
lab.
acha. हाँ. In
So
the last lecture, sir has explained all the numericals very sincerely and conceptually.
mhm.
We are satisfied.
Yeah.
Our doubts are clear.
Okay. So actually, today's discussion is more or less on the same lines only, same topics that were covered in the
It is on
first week.
the assignment one, na, sir. Week one
Yeah,
assignment.
but since Abhik has taken the you know some questions in the last discussion, I thought I'll make this as a revision type of class. So
Okay,
it will not be one-sided discussion.
okay,
Um,
okay.
we'll discuss whatever you know, and then I'll explain some things which I have learned over the period of time,
Yes,
and
sir.
then we'll proceed. So, Narendra, where are you from?
Sir, I am from Chandrapur, Maharashtra.
Oh, I am from Pune.
Okay, okay, sir.
I was
Bye.
I was I was in VNIT Nagpur for my bachelor's, so
Okay,
I
okay,
have
sir.
I have been in that area. How is it there now? It will be very
Uh,
hot, right?
sir, actually, by your name, I was thinking to ask. Your name
Achha.
is Maharashtrian.
No, that is okay. How is the weather in Chandrapur? Hot or cold now?
At present, it's cold because there
Okay,
was raining continuously.
yeah, that's good.
Yeah.
Otherwise, the
Otherwise, it's too hot.
the heat is too much.
But I
And
think Pune is very good atmosphere.
yeah, Pune is better. Pune and Bangalore are similar only.
Because I know that one. I have passed my graduation B from Walton College, Sangli.
Oh, yeah. So okay, so we have Kanishka also. Kanishka, can you introduce yourself?
So good evening. So my name is Kanishka Singh. I'm from Muradabad, UP, and I'm doing my bachelor's degree in electrical engineering. Um I'm in now fourth year. I'm third. My third year exams are happens in last week. Ended last week. So I'm doing
How was
this
it?
course.
How was it?
Good. Oh, sorry. It's last month, June, and result is going up.
Okay, you are from electrical, huh? Then why are you
Yes, sir.
taking mechanical course? Any reason or just like that?
So I'm doing honors degree, and I'm think that is it's good, because in some motors, power stations,
Mhm.
thermodynamics principle is also up. That's why um, I think
Yeah,
it's good.
yeah, true. Everywhere, not only in electrical, everywhere thermodynamics is there. It's just that we don't explicitly study in other fields, but yeah, it's it's everywhere. So yeah, Kanishka is there. How are you? All fine on your side?
Yes, sir. Yes, sir. Everything
Weather
fine.
weather good or still hot?
Yes, sir. It's midway. It's hot and rainy.
Okay,
It's
okay.
alternate days, hot and rainy.
Oh, like that, huh? Okay, we have Priyanka also. Uh, Priyanka, can you introduce yourself? Hmm. No response from Priyanka. Hmm.
Hello.
Yeah. Priyanka, tell me.
Uh,
Are you somewhere outside?
hello.
Yeah, I can hear you. Can you hear me?
Yes, hello. I am actually a 2019 passer student.
Okay. From where?
Uh, from Mangalore.
Oh, which department or discipline you have done your
Uh,
undergrad?
mechanic, Mechanical engineering.
Oh, so what are you doing now? It's been 3 years.
Yes, I was working. Now I have quit the job for the gate preparation. So that is why I joined this course.
Oh, yeah. Okay. That's actually one of the thing that I was planning to tell you because uh, after bachelor's you should look at this course from the competitive exams point of view because in GATE also I think from thermodynamics good chunk of questions are there, including other uh, like corollaries or extensions of thermodynamics like heat transfer, another power that what is it? IC engine, power plant engineering and all. Anyway, so I'll like regarding this today's topic, I'll try to give you some references, which will be helpful for your competitive exams maybe, uh, because I've been through that phase, so maybe that will help you. Anyway, so yeah, it's already 6:10, so I think we should start now. Uh, and yeah, so uh, let me introduce myself. My name is Akshay. Priyanka, you can mute yourself. I'll ask some questions in between, then you guys can unmute. So yeah, myself Akshay. I'm doing my PhD from mechanical department of IISc Bangalore. As I told you, I did my bachelor's BTech from NIT Nagpur, VNIT Nagpur. Then my master's from IISc, and now my PhD. So, yeah, so this discussion is a part of our TAship for the PMRF scholarship that we get. So, today's topic is primarily focused on your week one assignment questions. But since Abhik has taken, many questions last time, what I'll try to do is I'll mold this discussion in the form of, uh, you know, uh, revision class, or you may have some doubts after going through this week one lectures and studying some things on your own. Those things you can answer, you can ask. We'll try to figure out together. Wherever you have doubt or any clarification required during the slides, feel free to stop me in between by unmuting yourself. And I'll be asking a lot of questions. So I expect some answers from you. If you're not able to, I'll clarify them. So let's start then. So first of all, I hope you are all able to hear me properly and see the slides that I'm presenting here. Uh, if someone is not able to see, you can tell me. And if no one is telling, I'll assume that everything is fine on your end. So yeah, this is the crux of the concepts that you went through in the first week. Uh, First is the concept of control mass system. In later your specialization of this course, you'll be introduced to control volume systems as well. But we'll discuss at the later time about those things. First of all, what is control mass system? Uh, can any one of you, tell me? You can raise your hand or directly start also. It's fine. We are four only people here.
Hello, sir.
Yeah,
Mass of
Narendra.
the yes, mass of the system remains constant.
Okay,
Uh,
that's
and
the definition.
uh,
But
yeah, and there is no energy transfer. in this case.
Okay. Okay, then let me ask you one more question. Let's say this is your system. Let's say any heat exchanger or anything, any turbine or compressor, any component. So there is a mass flow in from this end and there is a mass flow out. Let's say mass flow in, mass flow out. So m dot represents it's a per unit time quantity, so mass flow rate. So now uh, in special case, in a steady state, uh, you have m dot in equal to m dot out. I hope everyone knows what is steady state. Steady state is a state achieved in the system when all the parameters or the state variables are independent of time. So therefore, whatever mass is entering in your system, the same mass will leave out. So now, can any one of you tell me, is this control mass system? Because the mass of the system of this box, it is constant. But is it a control mass system? That's my question. And this question is asked in various interviews after competitive exams.
Sir,
So,
no, sir, it is not a control mass in a case because mass is entering the device as mass is leaving the device, leaving the system.
but you said now mass of the system is constant.
But no, sir, mass is not remaining constant. Yeah, fixed in the system. Mass of the system remains constant in case of the control mass.
Actually, the correct terminology is identity of mass of the system remains constant. So in this case, what is happening is at every time step, new mass is entering and new mass is leaving the system. So this is not a control mass system. This is a special case of control volume system because the volume is also constant here. So anyway, leave that part aside. What is control mass system is a system where there is no energy interaction. That part you told correctly. But when you say the mass of the system is constant, you should say the identity of the mass of the system stays constant. And by identity means like I mean like whatever is the mass in the system, the same mass is there. There is no mass coming from outside. So that is the correct definition. Don't say just mass, say the identity of the mass. So yeah, that is one. Now, what is the zeroth law of thermodynamics? This was also covered in the week one lectures. Uh, Anyone can answer. I think more people have joined now. Uh, One more person has joined. So anybody can answer what is the zeroth law of thermodynamics if you have gone through the you know lectures that are there on the NPTEL site. It's explained there.
Uh, Sir, it concerned with thermal equilibrium, and it is
Okay.
a concept of measuring the temperature.
Uh,
Two
Again,
systems are in a thermal equilibrium with a third system. Then
okay.
they also in a thermal equilibrium.
Uh, Yeah, I mean, I think you understood what is the zeroth law, but that is not an exact statement of the zeroth law.
Yes.
The zeroth law of thermodynamics is basically it talks about first of all, anybody if asks you what is zeroth law, first thing you should tell is it is uh, regarding thermal equilibrium. So there are three types of equilibrium in thermodynamics or in anything, any natural process. One is thermal equilibrium, in which the temperature is the deciding quantity, which will decide whether it's a equilibrium or non-equilibrium. Sometimes there is, mechanical equilibrium, which is decided by the pressure. So if pressure in both sides or like different sides or different points of the system are constant or same, then it's a mechanical equilibrium. And third is chemical equilibrium, that chemical equilibrium is not part of this course. This is an introductory course for thermodynamics, I feel. Let's leave the chemical equilibrium, but after this, I mean, when you learn new concepts in this course, you'll end up with dealing with the thermal equilibrium or mechanical equilibrium. So, zeroth law of thermodynamics is basically, uh, if anyone asks you the statement, you can just draw like this. Let's say there is any system A, and it is in thermal equilibrium with system B. So that essentially means TA is equal to TB. Here T represents the temperature. And if system B is in thermal equilibrium with system C and its temperature is C, and one more important word you should not miss is, this is also asked in many competitive exams, these bodies A and B and C are in thermal equilibrium with each other separately. So you should not say if two bodies are in equilibrium with each other, it will be in equilibrium with the third. A and B should be in thermal equilibrium with each other, should be in thermal equilibrium with each other separately. Then you can say A and C are in thermal equilibrium. So based on this, the moral of the story is this law gives you a concept of something called as temperature. It is a quantity that you can measure and define thermal equilibrium based on it. So in some competitive exams, they'll ask you where do you use zeroth law of thermodynamics, or in some, like this question was asked to me also in BARC BARC interview, that you understood the zeroth law, that is okay, but can you explain the zeroth law in practice? So I told them in practice it is used in thermometers. Whenever you go to the doctor and you want to measure your body temperature, they put thermodynamics in your either in your mouth or in your armpit. So your body is A. Let's say, taking analogy from this figure, your body is A. The glass of the thermometer is B, and the mercury in the thermometer is C. So initially, this mercury glass and mercury within the thermometer B and C are in equilibrium. Then the glass comes in contact with your body, which is A. So after some time, your body comes in thermal equilibrium with the glass of the thermometer or the bulb in which the mercury is there, and eventually your body temperature is reflected by the expansion of mercury. So this is a very common example that everyone knows, that zeroth law of thermodynamics is used in thermometers or temperature measurement devices. But if anyone asks you how it is done, you should explain like this. You should treat your body as body A, the glass of the thermometer as a body B, and the mercury in the thermometer as body C. So if you explain this way, I think people will know that you understand what is zeroth law of thermodynamics. It's a very easy law to understand, but if you don't properly understood or properly explain it, it will be very difficult to explain in interviews. So anyway, moving on. Next part was intensive versus extensive properties. Anybody other than Narendra, you answered two questions. Anybody can tell me intensive and extensive properties? Any idea?
Sir, I have idea, sir.
Come on. MP Reddy, new person.
Yes.
Can you briefly introduce yourself before the answer?
My name is M. Penchala Reddy.
Okay.
Been working as assistant divisional engineer in Telangana State Power Generation Corporation.
Oh, nice.
I'm also pursuing PhD, sir, in JNT University, Anantapur, Andhra Pradesh.
Okay.
Teaching is my passion, sir. I have followed since 7 years onwards NPTEL course.
Oh, nice.
I have also then completed 7 to 8 courses, sir.
Okay.
Sir, intensive property means it is independent of the mass of the substance. That means size or extent of the system. It does not depend upon the mass, sir.
Okay.
It means it depends upon the mass of the system.
Okay. Can you give some examples of each?
Intensive property independent of mass of the substance means density, pressure, temperature, specific volume, specific internal energy, specific entropy.
Okay. What is let me ask, these questions are open to all. Okay. What is the viscosity of the system? Is it intensive?
Intensive, sir.
Okay. Brittleness?
Sir,
Brittleness?
brittleness also intensive, sir.
Okay.
Activity also intensive, no, sir. It does not depend upon the quantity of the, that is mass of the solid material, sir.
Okay. So let me be clear. When you say intensive, what are you implying? Is it independent of mass or independent of volume of the system? What is it, mass or volume?
What, sir? Intensive, sir.
Intensive is independent of mass or independent of volume?
Mass volume both are directly proportional, sir. When mass increases,
No. That is, you can relate to it in some sense, but the definition says it is independent of mass of the system. And one trick which can be useful for competitive exam is this: intensive starts with IN, so it's independent of mass.
yes,
So
sir.
remember that way. So yeah, can you please tell me your name again?
M. Penchula Reddy, sir.
What should I call you? Reddy is fine.
Yes, sir. Okay. Always, sir.
So yeah, Reddy almost gave the correct answer, but you should be careful. It is independent of mass, and volume you can relate, but that's not the definition. So
Sir,
yeah,
I said specific volume is the example, best example for intensive property, sir.
correct. That is because it is meter cube per kg, right? The unit. So in any quantity, if the unit is per kg, that is intensive property.
Yes.
That way also you can remember. Now I'll just move quickly because half an hour is almost up. What is a pure substance? Anyone? Just bullets. Just three main characteristics of pure substances. Anyone?
Sir, it is a chemically single substance, but always this single substance is not a valid, sir. So it is a chemically homogeneous and invariable chemical composition, sir.
Okay, yeah, that's good. It should be homogeneous throughout the domain. It should be chemical composition should be invariant. And one more thing is there. Can multiple phases exist in pure substance?
Yes, yes, sir.
Yeah, so these three characteristics, if you give, first is homogeneous, then there will be chemical composition invariant, and it is number of phases can be greater than one. So yeah, if you know these three characteristics, then you can you can say you understand pure substance. Then this concept of thermodynamic surfaces, we'll discuss about this more in the upcoming slides. So we'll talk about it there. Final important aspect of your week 1 courses was ideal gas equation. So can any one of you tell me what do you understand when you say ideal gas equation?
Sir, ideal gas, nothing but perfect gas, sir.
Pardon?
Ideal gas is nothing but perfect gas, sir. Meaning is same, sir.
Okay.
There is no internal forces between the molecules.
Okay.
The volume occupied by the molecules is infinitely small when compared to the dimension of that system, sir.
Okay.
So that is the ideal gas, sir, or perfect gas.
Okay. And one more thing is its properties depend on the temperature, that CPCV properties. But okay, that part comes later. Whatever you have said is fine. My question is, which is also asked in various multiple competitive exams, it is when real gas can be approximated as ideal gas?
Sir, high temperature and very low pressure, sir.
Why? First of all, let's say if the real gas is at very low pressures, why we can assume it as ideal gas? What is the physics behind it? Any idea?
Really, I don't know. At very low pressures means the space occupied by the molecule is very small, infinitely small, sir.
No, that is to that is I mean, not space actually. When the pressure is very low, the number of molecules in that system itself are very low, because pressure is nothing but average force exerted on the normal area by number of molecules of that system, or the number of particles, atoms, whatever it is. So when you reduce pressure, you reduce number of molecules in that system altogether to a very low quantity, and that's why their intermolecular forces of attraction also decrease, and that's why you can assume any real gas when it is at very low pressures as an ideal gas. Another condition is when the temperature is too high. So when the temperature is very high, what happens? The vibrations. See, when you increase the temperature of any system, the amplitude of intermolecular vibrations increases, and if the temperature is sufficiently high, the molecular vibrations overcome the intermolecular forces of attraction. So in that case also you can assume any real gas as an ideal gas. So these two questions are very favorite for competitive exams and competitive exam interviews also. Very commonly asked in bar, KISRO, anywhere, even in PSUs. So you should know these two. And ideal gas equation is, sorry, this slide is too much cluttered. I'll make sure from next time to use more slides. So this PV equal to nRT, that is an ideal gas equation. And yeah, so here N is number of moles, like P and V, I think everyone knows. P is pressure, V is volume of the system. N is number of moles, R is universal gas constant, and one more important thing is T, which is temperature. It is always in Kelvin. Many a time people make mistake about this. Sometimes by ignorance people put it in degree Celsius or Fahrenheit, but it is always an absolute temperature. Uh, there is a reason behind it, but that will come later in this course. But, make a habit of it that always you'll put absolute temperature, which is in Kelvin. And just to highlight what is Kelvin, 1 degree Celsius is 273 plus 1 degree Kelvin. So it will be 274 Kelvin. So whatever degree Celsius is there, add 273 to it, you'll get Kelvin. Now there is another way of writing ideal gas equation, which is PV equal to mRT. So in that case, M becomes mass of the system. Now in that case, this R bar will become, R bar is universal gas constant, which is true for all the gases, but it will become a gas constant for a specific gas that you are considering when you put PV equal to mRT. And for any gas, let me come in this corner. You can calculate R by molecular weight, dividing by molecular weight. I hope everyone knows the R bar, which is universal gas constant. The value is 8.314 joule per mole Kelvin. And when you divide by the molecular weight of whatever system you are considering, then you'll get the respective gas constant for that or that gas. And one more very important thing is, which is also not told often, because everyone studies ideal gas equation only for gases. Let me ask you one question. I'll ask it later when we discuss these thermodynamic surfaces. If I forget, remind me. Can you apply ideal gas equation inside the dome? And what is dome, that we'll discuss in the next slide. But this question was asked to me also in ISC, not everywhere, anywhere else. In ISC, I also took thermodynamics class in my first semester of masters. There, this question was asked: can you apply ideal gas equation in the dome? So we'll discuss this in this slide itself. So this thermodynamic plots of thermodynamic surface. Reddy, can you mute your phone? I'm getting some sort of interference. Hello? Yeah, fine. So we'll quickly go through this because it's already 6:35. Anyway, so this is also equal to surface only. You can say thermodynamic surfaces or plots. So basically, you take two independent variables and plot them for all phases for a pure substance. What I mean is, let's say this is my y-axis and this is my x-axis. And whenever you hear PV plot, that means your pressure will be on the y-axis and your specific volume in meter cube per kg. This will be on the x-axis. And let's say this is in Pascal. Whatever pressure in it, it can be Pascal, kilopascal, megapascal. Doesn't matter. It should be pressure. Now, this PV plot is, I'll show you in the next slide what it is for all the phases. But for this course, 99% of the time or 95% of the time, you will be dealing with liquid plus vapor mixtures. So I'll show the plot for that part only. So this is what we call as a saturation line between different phases. So here it is liquid and vapor. Now this line here, it will be a triple point line. Here it will be a critical point. One second, someone is knocking on my door. 1 second. So yeah, so this is what I called as dome earlier. It's not a standard term, but many times people call this as dome or hill or whatever. So my question is, can you apply PV equal to nRT in the dome? Can anybody answer this one? Dome means inside this part.
That
Tell me.
sir, we cannot apply PV is equal to nRT in the vapor dome, sir.
But we have vapor inside, right? We have liquid plus vapor mixture here, right? Liquid plus
Yes,
vapor
sir.
mixture,
But it
right?
is valid for only gas, sir.
But here vapor is also gas, no?
No, sir. But here it's a combination of liquid plus vapor, no, sir.
Okay.
Vapor which exists above the critical point is referred as the gas, sir.
Not really.
Yes.
I mean, you're saying gas cannot exist below critical point.
No, sir. Above the critical point, the vapor which exists above the critical point means above the critical point temperature, sir. That is 374.15 degree Kelvin. At that region, the vapor can behave as an gas, sir.
What is here? Outside this dome, what is here? In this region?
No, sir. No, sir. If you have to write the straight by touching the critical point line above that horizontal line, sir. Above that horizontal line, sir. Where
So
you have to mark the.
You are saying this
Yes, sir. Above that point.
here
Yes,
you are
sir.
saying
Yes, sir.
there will be a gas.
Yes.
Here it is also superheated vapor, right?
Sir,
Yes. This right,
Sir,
sir.
sir,
The
excuse me.
region
Yeah,
of the
Narendra, yeah, tell.
Sir, within the dome, there is a mixture of liquid and the vapor. Means it is a
Uh,
two-phase mixture. It is not a single phase. And
mm,
after this, and a saturated and a steam line, there is a
mm,
superheated and a steam, a superheated vapor. It is a vapor only. It is a one phase. We can apply the gas equation for the superheated steam and outside of this and dome. But we cannot any apply the this gas equation for this and within the dome. Is it is a
my,
two-phase mixture.
my
It is not
question is,
only
sir,
that is a vapor.
okay, fine,
sir,
fine. I think you know that you cannot apply ideal gas equation inside the dome, but
sir,
you
we
will
have,
be, huh? Come on, tell
sir,
me ready.
here we have also applied the ideal gas equation in the superheated vapor region with some
Uh,
error, sir. Is it
hmm,
correct, sir?
correct. So here basically we assume the superheated vapor as an ideal gas, which may not be true. There is a term called as correction factor. Uh,
Yes, sir.
it is, I think, denoted by Z. So in that case, your ideal gas equation becomes like PV equal to ZRT. But don't worry about this now because it comes in a later advanced thermodynamics course. This is not for your course, but yeah, if you apply ideal gas equation in the superheated vapor region, the underlying assumption is that you assume that superheated vapor is a ideal gas, and that assumption can be justified because when the vapor is superheated, its temperature is high, and as I told you in the last slide, when the temperature is high or the pressure is low, you can assume any real gas as an ideal gas. So that's why we conventionally apply ideal gas equation in this region, but there is some reality. There it's not a completely ideal. I mean assumption. It has some meaning because the temperatures are too high. Anyway,
Thank you, sir.
so yeah, let's move on. So this is the actual PV plot. I think the slide is not updated yet. Huh. Are you able to see the new slide? Hello?
Sir, yes, sir.
Yeah, so basically, this is taken from Moran Shapiro. This is a standard thermodynamics book. So if anyone wants to, learn more about this PV plots or any thermodynamic surfaces, you can refer to this Moran Shapiro book. It is available online freely everywhere. PDF is there. So anyway, this is a pressure and this is a specific volume. Uh, in thermodynamics, there is a convention that specific, this quantity which are specific, they are generally written with a small letter. So this is not a capital V. This is a small v. This is also very small detail, but you should know. So this is a critical point here, and this is a triple point line. I mean, you can call triple line also. So in triple line, three phases: solid, liquid, plus vapor. They coexist together, and critical point is a point beyond which only solid to vapor transition will be there. So no liquid phase beyond critical point. So these two critical things you should know. This region is a solid to vapor, which is called as sublimation. So solid to liquid is fusion, and liquid to solid is a solidification process you can call. But your most of the your course will be focused on this liquid plus vapor region. But you should know what all regions are there. That's why this you can you should understand. And these green lines are your isotherms, constant temperature lines. So one thing to notice, if I take, let's say, this isotherm, this line, first of all, this line is passing through the dome and now it's going out. So my question is, mm, when, I mean, where the temperature is high, sorry, wrong question. This is constant temperature line. Uh, my point is the direction should be like this. I mean, wherever, this direction will be there when your solid turns into liquid and liquid turns into vapor. So your isotherm is going like this, and reverse will be the case when your vapor is condensed into liquid and liquid is solidified into solid. So that time you will go in the other direction. So yeah, one more competitive exam question. Uh, let's say I'm talking about water only. So to define, like, at critical point, what all the quantities that are fixed. What I mean is, uh, critical point temperature is fixed, critical point pressure is fixed, and critical point specific volume is also fixed. So when you talk about critical point, these three quantities for a given substance will be fixed, pure substance. But when it comes to triple point, you can only have temperature of triple point, pressure of triple point, but this specific volume of triple point is not fixed, and that is why you are getting a line here. And since this is a volume axis, you can justify the volume changes uh, even if you are at triple point, the volume will change, but your triple point pressure and triple point temperature will be constant. Whereas if you are at critical point, your pressure, temperature, and volume, all the three parameters will be constant. But on the triple, that is constant, all three are constant at critical point, and only two are constant at triple line point. So this question is also asked many a times in interviews. So you should know about this. Then actually we are short of time, so I'll just show you the actual TV plot. This is for water. I think the slide is updating. 1 second.
Sir,
Are you able to
sir,
see the TV? Bolo, ready. Come on, tell me ready.
sir, a small question, sir. That's
Yeah.
I have doubt actually. I read some books. I read in books there.
Mm.
Particularly in Indian books, so they have to given above the critical point, the liquid suddenly vaporized into suddenly liquid converts into vapor. I think this is not correct, no, sir.
Actually, what they are trying is, what they are saying is, see, I mean, you should read that text in full context. So most of the time, how they explain the PV plot is, they'll start with ambient liquid in a closed container, and then they'll keep on adding the heat to that control mass. But what happens is, actually my slides are loading very slowly. I would tell you what is happening. Let's say this is not a TV plot. This is PV plot. I'm just answering your question. You know that there is a dome like this, and inside this dome there is liquid plus vapor mixture. Let's say we are above the triple point line, so don't consider the triple point and all. This is purely liquid and vapor transition. So what happens? And the isotherms are like this. You have seen they are like this, right? So when you increase the temperature, what is happening is, essentially these are the temperature isotherms increasing direction. So your latent heat of vaporization, which is given by this length, which is denoted by generally HFG, it is shrinking as you go up. See, here the length is this long, here the length is this long, and this length represents your liquid to vapor transition. So what happens? Let's say you are at the critical point here. You keep on adding heat to your system, and you reach your critical point. So here what happens? There is no phase change kind of phenomenon happening, because you're at the saturation line of that pure substance. So here there is direct flashing into the vapor. This happens like supercritical boiler. This is one of the one of the very important application of this phenomena. What happens is, if you do this way, if you heat the fluid above critical point, you need to provide lesser boiler volume. So supercritical boilers are smaller in dimensions as compared to your conventional phase change boilers. So I think I'm going off the topic here, but the point is, if you are at critical point or above critical point, your liquid will directly flash into the vapor. There is no phase
Sir,
change.
sir,
Yeah,
sir,
tell me, Reddy.
sir, here at the critical point, we have to draw on the line continually, sir. There is no discontinuity. But below the critical point, that is a subcritical state, sir. Below that, there is a phase, there is a appearance, sir. But above the critical point, we have to draw on the line continuously. So,
Mm,
as per that line, I have to think there is a continuous vaporization of a liquid. That means there is no sudden flashing of the liquid into vapor, sir. Is it correct, sir? As per
no, no,
that line, sir, I don't
no,
know
no.
actually.
See, in this region, this
Sir,
dome region, there will be gradual boiling. So you can see, boiling taking place. If you have any camera or anything inside the boiler, you can see liquid boiling and then converting into the steam if it is a water. But here, let's say you are in this region above the critical point. Here, as soon as the liquid water enters boiler, you can't see any boiling or anything. It will just convert into vapor. That process is very fast. It's like flashing only. But I mean, are you getting my point? There is
sir,
nothing like boiling there.
sir, this line is a continuum, sir. You have to draw the line by touching the critical point, or you suppose we have to draw above the critical point. The line
Mm.
is continuity means where the liquid converts into vapor. We don't know, sir. That is the designer secret. Actually, I have worked in 800 megawatts also, sir, 7 years.
Mhm.
Uh, there also where it has for the liquid into vapor, we don't know, sir. That is actually some BHL people, engineers, they told me that is the design secret. We don't know, but there is a continuous. There is
Okay,
no
okay.
breakup.
Hmm.
That's why I'm
Okay.
asking you, sir.
Hmm. ठीक है. We'll discuss this later, ready, because I think we are, short on time. We have not gone
Okay,
to main part of our discussion, which was,
okay, no problem.
yeah. So this is a TV plot. Uh, it is for water. So here, your y-axis is temperature in Kelvin. It can be in degrees Celsius, no problem, and specific volume. Here also, you'll have a triple point line, not a single point. You can call it triple line, whatever. And then there is one more PT plot. So here, you cannot see phase change. Phase change not visible here, because since phase change is constant temperature and pressure process. So this is also asked in many places. Show me phase change process on PT plot. So you just have to say it can't be shown because this is a PT plot. During phase change, P and T are constant. Volume changes, but since this is a PT plot, you cannot show volume here, and therefore, let's say if I am here when the liquid is converting into vapor, I cannot show you phase change. During the whole phase change process, the phase change process will be shown by a point here. This is one of the important question that is asked at many places. Here, critical point is still a critical point, but triple line now becomes triple point. This is also important point you should remember. On PT plot, triple point is a triple point. It's not a line. So these are the surfaces. This is actually a 3D representation of whatever we discussed in 3 different plots. Here, this is a temperature axis. This is specific volume axis, and this is pressure axis. So in this slide, you can see there are 2 different PVT plots for water and non-water. In case of water, it's matlab, water has an inherent property of showing anomalous behavior between 0 to 4 degrees Celsius, and therefore this whatever you are seeing the difference between these 2 figures at this point, it is because of the inherent nature of water. But since water is the most commonly used fluid on earth, we should know that there is something different in PVT surface of water. Actually, one more thing is, if you see the PT plot, this is not for water. That you should remember. For water, this line will be something like this. This SL, solid to liquid phase change, it will have some different slope. For this line, the slope is in this direction, right? But for water, it will be having in this direction. So that is one important question. This is for water. Now we'll quickly go through some examples. Actually, this was my main point of the talk, but anyway, we are slightly late. Now here, what I'll do, I'll give you brief idea how to solve these questions. I'll be very quick because you might have some idea about this because Abhik has already taken a class and you have attended the courses, video lectures also. So one of the critical point in solving such problems is you should be able to figure out which type of surface plot you should use. Here you have options of either using PV plot or PT plot or TV plot. In my experience, generally TV plot is not used multiple times. So like whenever you are solving a problem, it's better to start with either PV or PT. Now here you can see like pressure, volume and temperature are there. So you can start with anything, but the problem is on PT plot, you cannot see phase change. So it's better to start on PV plot because here we have volume also. In one of the question, volume is also asked. You cannot decipher volume in PT plot. So it's better to start with PV plot. So let's say this is a PV plot. And this is our dome. And as I told you earlier, most of the time in this course, you will encounter with liquid to vapor transition. So we'll focus there only. And this question relates to that part only. And most of the time it will be water. So now let's say first part of the question. And you all know the isotherms on the PV plots are shown like this. So this line is a constant temperature line. In this case, it will be 150 degrees Celsius. Now the question is, when the temperature is 150 and pressure is 100 kPa, what is the phase of the water? Now, I think all of you has access to steam table, and if you don't have steam table, I would it's not that hard to get a steam table nowadays. You can just Google steam table IIT Bombay, you'll get a PDF. Or if you are reading any standard textbook, you can just go and I think at the end of any standard textbook there will be a steam table, or you can purchase a steam table. It is available as on its own also. So for this example, since we are at temperature 150 degrees Celsius for both first and second case, we'll just look at the saturation pressure corresponding to 150 degrees Celsius. Now you may ask why? Because that saturation pressure will give you this point. And if you know that like if your pressure is above this point, it will be in this liquid region, and if it is below this point, it will be a vapor region, superheated vapor. So if you have used the steam table, you'll know that steam table is given in two formats. One is temperature versus saturation pressure, and the other format is pressure versus saturation temperature. But here we need saturation pressure. So we'll go to the temperature based saturated water and steam table. Here, if you go, you'll see the saturation pressure is roughly 476.16 kPa. So now, and this value is here. So this line represents 476 kPa. So now, in first part, the pressure is given as 100 kPa. So you know on this axis, if this is 470 kPa, 100 kPa will be somewhere here. So in that case, it cannot be subcooled liquid. It cannot be two-phase mixture. What it can be is somewhere if that constant temperature point touches this pressure line. So that's why it is in the superheated vapor region. So the first, first temperature pressure condition is for a superheated vapor. Now you can answer the second question in the same manner. Now here the pressure is 800 kilopascal. Yeah, our saturation pressure is 470 kPa and your pressure is more than 470 kPa. Let's say it is 800 here. The diagram is not to the scale, it's just a schematic, so bear in mind that. So now if it is 800 kPa, again it cannot be liquid plus vapor mixture, because if that has to be there, the pressure should be 470 kPa. Here pressure is more than that. So it cannot be liquid plus vapor. It cannot be vapor. It can be only subcooled liquid, or compressed liquid they call it, because the pressure is higher. So you can answer this way, these type of question. I'll leave the third question to you to answer, because it's a slightly tricky part. If you can't find the answer, you can, next session we'll meet next Tuesday. You can ask me there. But the trick is, see, you should look at whenever the volume comes into picture. The first part is you should look at what is the volume of fluid here and what is the volume of saturated gas here. So these two quantities you'll get from steam table again. So if this volume lies in between somewhere here, that means this is a two-phase region, and if this V is greater than Vg at 150 degrees, it will be a superheated vapor. So I'll leave this exercise up to you. It's a simple exercise. I have given you a hint also. You can figure it out. Answer, if you can't find, ask me next time. We'll discuss, or I'll give you the answer. So this is also a similar question. Here, one trick is, whenever like this X here represents dryness fraction, and it is defined as mass of vapor by mass of vapor plus mass of liquid. When I was in my undergrad, I also used to get very confused by this definition. Mostly like whether there is a mass of vapor in the numerator or mass of liquid. So like the key to remember this is in its name itself. So dryness, let's say you have a liquid and vapor. What is more drier? It's vapor. The liquid is wet. So by that logic also you can remember that numerator is always mv, not ml. I remembered it that way. It might help you also, or you can have your own, trick to remember. So now here they have given dryness fraction as 0.6. So indirectly this is a hint that this is liquid plus vapor mixture. And if it is a liquid plus vapor mixture, let's say we are again going to the PV plot. If it is a liquid plus PV mixture, it will be lying somewhere here inside this tube. So what you can do is look up in the steam table where Psat is 650 kPa. So corresponding temperature will give you T4. And if you plot this here, this is your 650 kPa line. And dryness fraction is 0.6, means you have 60% vapor. So it will be somewhere here. Like if this is the midpoint of this line, it will be somewhere, right to the midpoint, since it's a greater than 0.5 value. So you'll get T4, and I have done that calculation. If you go to T4, you'll get 162 degrees Celsius roughly. There will be some point plus or minus something, but it should be 162 degrees Celsius. And now calculation of volume, again I'll give you a formula, you can work it out on your own. So here Vf is a saturated liquid volume, specific volume we are talking. It will be here, Vg will be here, and these two values Vg and Vf you'll get from steam table, and you plug in the value of dryness fraction, you'll get the volume V4. So that is also easy. It should be around 0.176 meter cube per kg. You just work it on out yourself. If you are getting this closer to this volume, it's fine. If not, then ask me next time. I'll tell you. Check your calculation. Mostly it will be a calculation mistake. So these type of questions will be there in which some property will be missing, or they'll ask you in which region this P and T plot points lie. Such type of questions are there. Use steam table. Always draw PV or mostly PV plot you can draw, and draw an isotherm like this, and you will be in a good shape. And just figure out where do you think your point may lie. So this is a trick to solve such questions. This question is again similar, but here the trick is temperature is given and pressure is given. So here, instead of going for a PV plot, it's better to solve it by PT plot. So as I shown you earlier, this is a PT plot and it's a water. So keep in mind, for water this line is like this, and this will be a triple point line, triple point, sorry. This will be a critical point. This will be a roughly PT plot. So here you do one thing. Your first point is having pressure 550 kPa and temperature minus 30 degrees Celsius. Plot this point on this PT plot. You'll be ending in this region somewhere. This, like, you'll be ending in solid region. And when you plot your second point with pressure, same pressure 550 kPa and temperature of 140 degrees Celsius, you'll be in coming into this region. So this will be your second point. And since it's a constant pressure process, it will be like this. So now your job is to figure out whether this point 2 will be in liquid region or vapor region. I leave this to you to figure it out, but it's also very simple. Hello?
Sir.
Reddy, tell me.
Sir, sir, for this question, answer A is right, sir, because simply triple point pressure is 0.61 kPa, which is here given less than 0.61 kPa. That is it correct, sir?
This is 550 kPa.
Okay, sir.
Don't make the mistake of units. See, in GATE exam, I'm telling you, I have given GATE twice, and I know many people who have given GATE with me. In GATE exam, people mostly make silly mistakes, and this mistake of uh, taking wrong units in coming under pressure, that's a very common mistake for any competitive exam. So just be patient, read the question carefully, and avoid such mistakes. Okay, since some of you are preparing for GATE exam, I'm telling you, in GATE exam, if you are honestly studying, you'll do only simple mistake only. Your concepts will be very clear, but on the exam day, you'll be making such a stupid mistake, you'll be blaming yourself. So my advice to you, all of you, not only Reddy, all of you who are listening, just be patient, just take care of units and just take care of your formula. Whatever you're using, is it the right formula for that case? If you make sure of these things, your silly mistakes will go down. So like implement this in your practice tests and wherever you are, solving problems. So yeah, Reddy, you should figure out where is this second state. I'm telling you the answer is not first because
Okay,
whatever you just said, it is wrong because it's the KPI. So yeah, okay. So now going to the
Yes, sir.
yeah. So now
I
this
have
is
happy sir today.
oh, you are leaving, Reddy.
No, sir.
Okay, give me 5 minutes. I'll finish. I know I am over time. Just give me 5 minutes. This question is you'll face these type of questions more in upcoming sessions. So this is a very simple question or simple questions with respect to the whatever questions you'll be facing in the next upcoming classes. Here, uh, one hint is like they are telling you to plot it on PV diagram. So what you do, don't go for calculation initially. Just draw a PV plot, and here it is given that it's a piston cylinder assembly. So it's a piston cylinder, typical piston cylinder assembly. This is a piston and this is the cylinder. So here there will be some gas. Yeah, so here they have not mentioned any liquid or anything. So we'll assume this as a only gas, single phase flow, single phase system, not a flow, sorry. And the first process, it is a PV equal to constant process. So it is something like PV equal to C. C is the constant. So now in your 10th, 11th, 12th, or those classes, you might have seen when your xy is equal to C, if you plot it, you will get such curve because x is proportional to the 1 by y. So whenever y is high, x will be low, and whenever x is high, y will be low. Similarly, here only you can see same logic. So you'll get such curve here. So now just make sure which point is 1 and which point is 2. So at point 1, pressure is 1 and volume is 1 meter cube. At second point, pressure volume is 0.2, pressure is unknown. But you can calculate P2 V2 equal to P1 V1, and you'll get P2 as the volume is decreased by 5 times, so pressure will increase by 5 times, so you'll get 5 bar. So your pressure 2 is high, so this will be your 0.2 and this will be your 0.1, and since it's 1 to 2 process, the arrow will be there. This is shown here as a quasi-static process. Since we are in a thermodynamics class, you should know what is quasi-static process. It's an process with infinite.
Can you be louder, please?
Okay. Okay, I'll take the mic. Were you not able to listen to me the whole time? You're telling me this at the end. Anyway, uh, I'll try to be louder. So this quasi-static process is process with infinite thermal equilibriums, but slightly, each after achieving each thermal equilibrium, you slightly disturb the system. So that's why this quasi word is slight change. So yeah, so this is process 1 to 2, and second process 2 to 3 is a constant pressure process, so it should look like this, and its volume 3 is V3 is 1. So you can see V1 and V3 are same. So if you plot this way, this should be your third point, and this is your direction, and this is a constant pressure process. This is PV equal to C. And now process 3 to 1 is a constant volume. See, they have not mentioned any initial volume like V3 is this much, or any P3 is this much. So they have given you hint in the second process itself that your V3 and V1 will be same. So and since it's a constant volume process, you'll be ending up like this. So this is your cyclic process. Some of you may not know what is cyclic process, but as the name suggests, it's a cycle. So your initial point and your end point for the cycle, they'll be coinciding. Then it is a cyclic process. You'll learn more about this in the next classes, but I'm just telling you, this is how you can draw any cycle or any process on the PV plot. Some steps are, first, just make sure, is it a single phase flow or liquid plus vapor mixture, and then go on, take each process at time and just figure out what is the starting point and what is the end point and which direction you will be going to that process. So this is one. This question actually is quite this will need some time. So what should we do? Should we discuss it now or should we discuss it later? If you guys are okay with it, I'll discuss it now, or maybe we can discuss it later. So what do you suggest?
Sir, in the next class.
Oh, Narendra is in hurry to leave. Huh? Okay. So yeah, anyway, I think we overshoot the time today. So what I'll do, I'll discuss this question next time. But you know, it's a interesting question, and I think in your NPTEL lectures also, Professor Suman Chakrabarti sir, he took one of such example. Anyway, we'll discuss this next time. So if you have any questions, I'll share these slides with the NPTEL team. Maybe they'll give you the slides, and this video will be uploaded on YouTube. So you'll be able to see this. If you miss this, you can go to YouTube and check it out. And if you have any doubts, we'll meet next Tuesday and we'll discuss at that time. So thank you for joining, all of you. And next time, just make sure you join on time so that we don't get overshoot the time. And yeah, so should we stop now? I think Narendra is already gone. Oh, he's
Thank you very much, sir.
Okay. And yeah, others also participate. Today, Narendra Reddy and few of you are participated who joined initially. But it will be more healthy discussion if all of you participate. And yeah, that will be my feedback. And let's stop now, and we'll meet again tomorrow, next Tuesday. Okay. Bye then.
Today we have to learn some new things which are not exist in the textbooks, sir. From yourself only we have to grab. Very thankful to you, sir.
Oh, thank you, Reddy. And yeah, hope to see you again next Tuesday. Please join on time, and so that we can leave on time. So okay then, chalo. I'll stop the session, and bye bye. Have a good night. Bye.
Thank you very much.
Okay.
నాన్న ఇప్పుడు కొట్టడానికి ట్రై చేస్తాడు. ఇప్పుడు ఇంకో క్లాస్ ఉంది. ఇదేంటి ఈ క్లాస్కి వచ్చా 6 to 7